The motivation of this demonstration stemmed from the fact that we were interested in studying kinematics with the concept of kinetic energy to explain the reason behind the perceived phenomenon. We believe that archery, using a toy bow and arrow, would be exemplary of our thoughts, as intuitively, the further the bowstring is pulled back, the faster the arrow is propelled. This later becomes evident through the greater initial velocity later observed in the experiment. Alternatively, we can analyze the kinetic energy released using the following formula. It can be said that kinetic energy is proportional to the square of the velocity. If speed is doubled, we would expect kinetic energy to quadruple, and so on. The intent of this experiment was to model doubling the speed by varying the deformation of the bowstring to where we observe the initial velocity doubling. However, due to this task being difficult to replicate in action, we observed a greater difference in velocity, not necessarily double the first trial. In terms of the experimental setup, our partner Preeti decided to do the demonstration of shooting a bow utilizing different pull strings. The experiment took place in her backyard. As a side note, this experiment was done completely COVID safe, where our group opted to have only one member perform the experiment as to reduce spread of COVID. The first trial consisted of Preeti pulling the bowstring with minimal effort to demonstrate a smaller initial velocity. In the second trial, Preeti increased the pull strain, or in technical terms, attempted a full draw to show a faster propelled arrow. If this is not clear, Preeti wore different colored shirts in the two videos to be able to easily differentiate between the two. Each trial was analyzed separately in the video analysis program, and a graph measuring x velocity versus time was generated for both situations. The bottom component of the graph represents the position versus time. The top component of the graph represents x velocity versus time, which was derived from the position data. Both graphs exhibited constant velocity just after the release of the arrow. The average of the points after the release time was computed to represent the initial velocity of the arrow. This can be justified by the fact that no net forces are acting upon the arrow in the horizontal direction. Therefore, by virtue of Newton's first law, the arrow would continue its motion in the same propelled direction, moving at a constant speed. In another manner, one can manifest the law of conservation of energy in that the total energy involved in the process of shooting a bow remains constant over the entire duration. Energy, however, can transform from one type to another or from one part to another, which is what we witness in the experiment. The bow stores elastic potential energy as the arrow is drawn back. Once it is released, the potential energy of the stretched bow is converted into kinetic energy of the propelled arrow. In the first trial, where the pulling strain is minimal, the observed initial speed was 9.048 meters per second. Therefore, the observed kinetic energy was 0.29226 joules. In the second trial, where the pulling strain was the highest, the observed initial speed of the arrow was 12.015 meters per second. The observed kinetic energy for this trial was calculated to be 0.51536 joules. The trend shows that the more a pulling strain is applied to the bowstring, the more kinetic energy is produced overall.